Hello everyone, I'm Yang Liu from Shanghai Jiao Tong University. Today I'm going to talk about my work on latency robust control of high-speed signal-free intersection. It's a joint work with Professor Zhongping Jiang and Professor Li Jing. Recent progress on connected and autonomous vehicles, or we can call it CAVs, motivate high-speed signal-free intersections. With the help of V2V and V2X connectivity, CAVs have low response time and can cross intersections at high speed. The safety and efficiency of intersections heavily rely on the quality of communications. However, communication is not always perfect due to some limitations. Even small latency can cause instability in dynamic systems and further affect the efficiency and safety. Big distance of latency causes the delayed state observation. When the vehicle accelerates as subject to bounded uncertainty, the latency can increase the uncertainty. Motivated by this, the main questions we ask here are: first, how to design a vehicle coordination algorithm that is robust against communication latency, and then how to quantify the relation between communication latency and capacity. I will reduce it in the following 4 parts. First is the problem formulation. Consider the neighborhood of a two-direction intersection. We label the two orthogonal roads as 1 and 2. The states of the intersection is described as the positions and speeds of each vehicle in the intersection. Our task here is that assume that trajectories of all vehicles in front of vehicle I have been optimized and fixed. Then how to optimize the position and speed of vehicle I. Control input is the sequence of target speeds of each vehicle. The control input of vehicle I depends on the positions and speeds of vehicle I and vehicle I-1, which is the leading vehicle of vehicle I. We denote the length of latency by theta. Then we have the state that the RSU receives at time t is the positions and speeds of all vehicles at time t minus theta. When the RSU received the state of the vehicle, it first estimates the state of the vehicle after a time of theta when the vehicle receives the control input. Then it predicts the states at next time step. By the safety constraint, a safe and optimal action is obtained and sent to the vehicle. The vehicle receives the control input and begins adjusting its speed. We have two focuses here. First, propose a controller which is robust against communication latency and satisfies the safety constraint, which lower bounds the headway between vehicles. For the vehicles on the same lane, distance between two vehicles have to be larger than the minimum headway for the same lane times the speed of the vehicle behind, which represents the safe distance of the same lane. For the vehicles on two orthogonal lanes, the distance between two vehicles have to be larger than the minimum headway for the orthogonal lanes times the speed of the vehicle behind, which represents the safe distance of orthogonal lanes. And then we evaluate the capacity of the intersection. Here we come to the control design part. We have 2 parts here, estimator design and controller design. First, for the estimator design, given the multiple parameters, latency and speed uncertainty, and observed variables, the state and the control input, we estimate positions and speeds at time t plus theta. For the speeds, because the vehicle follows the control input at time t minus 1, then we have the speeds at time t plus theta is ut minus 1 with uncertainty. For the positions, we assume that the vehicle moves at a constant acceleration or deceleration. Then we have the estimated position based on the state information and the control input. After the estimation, we have to predict the states at next time step, which depends on the estimator and the control inputs at time t. We show that the length of the interval of the predicted position is a constant, which is 2 times theta plus delta. Then we come to the controller design. Given the model parameters of latency, speed uncertainty, time step size, maximum acceleration, minimum allowable headway, and observed variables, positions, and speeds, we determine the target speed of each vehicle at each time step. The predicted positions of the vehicles have to satisfy the safety constraint, as is to make the distance of each two vehicles safe. The objective function for vehicle I is the difference of the minimum possible distance between vehicle I and vehicle I-1 and the safe distance, which is denoted by the minimum allowable headway times control input of vehicle I, just as the picture shows. Finally, we can obtain the control law. And the information is the state information of vehicle I and vehicle I-1. Consider the limitation of acceleration and deceleration. We have that the feasible control input time t is within the change of speed limited by acceleration from time t-1. Then we have the controller, which obtains the ut such that the lambda is minimal and non-negative. Note that lambda is linear with respect to u, so the computational complexity is quite low. Then I will introduce the properties of the proposed controller. Here is the safety criteria for one-time step. The existence of the safety control input depends on the following conditions. First, there exists a safety control input U of t if and only if the following condition holds, which means that vehicle I must be able to keep the safe difference from vehicle I-1 when it takes the maximum deceleration. And then there exists a safe control input U of t such that vehicle I is able to keep the minimum allowable distance from the leading vehicle if and only if condition 1 and the following condition holds, which means that while ensuring safety, vehicle I also must be able to keep the distance from vehicle I-1, which is smaller than the minimum allowable distance, when it takes the maximum acceleration. Next, we come to the safety criteria for time series. Consider the observed initial state and initial control input. There exists inputs for all subsequent times if the following conditions hold. Part A means that condition 1 holds for initial states, and part B means that if for time t condition 1 holds, then for time t plus 1 condition 1 also holds. At it from time t, if vehicle I-1 takes the maximum deceleration and the vehicle I takes the maximum acceleration, then at time t plus 1, they can also keep a safe distance from each other. Then there exists a safe control input such that vehicle I is able to keep the minimum allowable distance from a vehicle I-1 at all times if condition 3 and the following condition hold. Similarly, part A means that condition 2 holds for initial states, and part B means that if for time t condition 2 holds, then for time t plus 1 condition 2 also holds. Therefore, we can get the form of the controller when condition 1 and condition 2 hold, which means that vehicle I is able to obtain the minimum allowable distance from vehicle I-1. At this case, lambda is able to equal to 0. Then we can get the formula of the control input. When only condition 1 holds, then the vehicles are only able to keep the safe distance. In this case, lambda I is always positive. Then we can solve the U of t such that lambda is minimal. When neither condition 1 nor condition 2 hold, it is unsafe. Finally, we evaluate the throughput. Here, we treat the problem from microsite to macrosite. The crossing time interval is d, and the minimal headway is h. Then, capacity F of the intersection is lower bounded by 1 over d plus h. Then, under the situation that all the vehicles are able to keep satisfy condition 1 and 2, F is lower bounded by the maximum allowable speed over the length of the positions interval plus the safe distance. And last is the conclusion. First, we designed a controller that coordinates vehicles in the high-speed signal-free intersection. And then, controller is robust against communication latency and ensures safety. And finally, we studied the relationship between latency and capacity. And our ongoing work is, first, we try to extend the intersection to a more complicated case, which have 12 directions, including turning. And then we study how to determine the parameters by simulation in Sumo. And that's all. Thanks very much for your attention.